we'll continue with the previous video. That is, if the error is of first kind, that is, for, if the S2 is transmitted and the decision is taken in favor of S1, then we can say that X1, which is nothing but it is affected by the Gaussian noise. Therefore, the probability density function of the random variable X1 given that symbol 0 is transmitted is given by the conditional probability. The conditional probability is given by f of x1 when x1 is the received signal but the transmitted signal is 0. This is the definition of conditional probability, is equal to 1 by root of pi into n naught exponential of minus 1 by n naught x1 minus s21 the whole square. See, whatever the equation we have written in the equation number 4, it is given as per the probability density function of the additive white Gaussian noise, that is the Gaussian process. So as we know that whatever the variable we got x1, it is nothing but the Gaussian random variable. Therefore, it can be represented by the its probability density function. So already we have given what is the probability density function of a Gaussian random variable. So it is 1 by root of 2 pi sigma, that is sigma is nothing but your variance, then exponential of minus of x minus mu divided by 2 sigma square. Mu is the mean of the random variable. So when we take this one, we know that what is the variance. So variance of the noise is equal to sigma square is n naught by 2 and mean is simply mean, already we have seen mean of the correlator output is simply Sij, that is the coefficient. So here S21 is the coefficient. So S21 belongs to symbol 0. So we have written what is S21? S21 is simply minus root EB. Therefore, when you substitute this in the equation number 4, we get the equation number 5. Now here, so this is what the received signal is. So this is the conditional probability density function of the received signal x1. Now when this error will happen, when this conditional probability density function falls in the region of z1. So what is the region of z1? It is limited from 0 to infinity. Therefore, when we take this as p10, p10 indicates that probability that decision is taken as 1, but it is the actually symbol is 0, actually transmitted symbol is 0. So therefore, the integration is taken over the 0 to infinity, because it is this probability density function is falling in the region of 0 to infinity. Therefore, the error has happened. Now when you take this one, so again when you just evaluate this integral, so you put z is equal to root of 2 pi n naught into x plus root eb as z. This step is done just to simplify the equation p10. So when you do this one, you will get equation number 6. Equation number 6, in the equation number 6 we have substituted z, and we have, you can see when you substitute z, the limits of integration also changes. So limits becomes root of 2 eb by n naught to infinity. So this above equation why we have changed this equation into equation number 6 is because we have a whenever we have a Gaussian process, Gaussian distribution. So Gaussian distribution, it can be represented in the form of Q function. That is, simplification is done in the form of Q function, because Q function is nothing but it gives the area of the tail of the Gaussian random variable. That is, so what is Q of x? It is simply 1 by root of 2 pi integration of x to infinity exponential of minus t square by 2 into dt. So when you compare this Q of x with the above equation number 6, you will get what is the Q of x. So we can write equation number 6 in the form of Q function as Q of root of 2 EB by n naught. So this is the whatever the equation number 7, it is nothing but the probability of error. What is the probability of error? Probability of error is nothing but the transmitted signal is 0, but the decision is taken in the favor of 1. So this is this will give you the how much the error has happened, that is how much is the probability that error will happen, that is if 0 is transmitted the decision is taken in favor of 1. So similarly we can calculate the error of second one, that is if the transmitted signal is 1 and the received signal is and the decision is taken in favor of 0. So as both we are assuming that both the signals, that is 0 and 1, both the symbols are equiprobable, that is they are sent with the equal probability. So the probability of error for P01 is remains same, that is in average we have the probability of error as q into root of 2 EB by N naught, that is for both the cases, for both the type of error the probability of error remains the same. So now this is what the probability of error gives. So how to reduce the probability of error? So probability of error can be reduced if we increase EB, that is the what is EB? EB is nothing but what? EB is nothing but the energy in a bit, energy per bit. So per bit how much energy we are transmitting, so that is nothing but your EB. So when you increase EB, so for specified amount of specified N naught by 2, so average probability of error will get reduced. Now so this is power spectra of binary PSK signal. Next, so this is so derivation is out of scope, so we'll just have the glance at the equation. So the power spectra is given. So power spectra, it is we can see in the figure, so it is symmetrical about the vertical axis, and we can see that with sin square pi TB into f limited to maximum value of unity. So this is what the power spectra of BPSK looks like. So this ends the first topic of the module 3, that is binary phase shift keying.